Okay, so hi there, folks. We're in our next video in the introduction to statistics, and we're going to continue what we have started in our lessons in probability. Here, we're going to talk about random variables and probability distributions. So let's start with the introductions. So we will consider this illustration. Okay, the following table gives us the frequency and relative frequency of the number of children in all 2,000 families in one particular town. So we're going to consider this example. So there are 2,000 families who were surveyed, for instance, and how many families have zero children? We have 30. How many families have a single child? We have 470. How many families have two children? 850, and goes on until four families. So it all sums up to 1,000, and we have the relative frequencies, okay, of them. So we have 30 over 2,000. So we have 0.015. For one children, we have 470 divided by 2,000. We have 0.235, and so on, all of them summing up to 1. Okay, so we're going to consider this case, and we will be, say we're going to imagine, suppose one family is randomly selected from this population. Okay, so from this certain population of one small town. So the process of randomly selecting a family, okay, is what we call a stochastic experiment or a random or chance experiment. Okay, and in this particular example, we're going to let X, okay, big X, let's call it so that it will be short. Big X denote the number of children in the selected family. Okay, so therefore, if that's the case, X can assume the values of any five possible values. Okay, it can start. Why is it five? Because we will start with zero. Okay, we can have the value of zero, as in we got a family, or when we chose, or when we select, randomly select rather, a family. It's possible that we can have a family with zero children. So we have five possible values, that is 0, 1, 2, 3, and 4. So listed in the column here on the table. So the value assumed by X depends on which family is selected. Okay, so this value depends on the outcome of this random or stochastic experiment. Okay, so hence this X is what we call a random variable because it's taken from one random experiment. So in general, a random variable is denoted by our big X or big Y. Okay, so let's give the definition and types of random variables. Let's start with the definition. So a random variable, okay, it is a variable, sorry about that. A random variable is a variable whose value is determined by the outcome of a random experiment. Okay, in technical terms, we call it's a function of every experiment you do. There is a certain outcome that will come out, but let's just imagine that a random variable is just a variable taken from a random experiment. Okay, I believe that's a definition by Alan Blumen. So let's take a look at the types of random variables. We have two. We have a discrete random variable. So this assumes values that can be counted. Okay, so these are values that can be counted. We're going to give examples later in the next slide. And we have number two, which is number one, which is number two. We have continuous random variables. So these can assume any value contained in one or more intervals. So it's not it cannot be counted. Usually, continuous random variables are the ones being measured. So the possible number of values that a continuous random variable can assume is infinite. Okay, so there are infinite number of values that a continuous random variable can assume. Since given an interval here, for instance, let's just imagine an interval of 1 to 2. So we can have 1 half, 1.5 in between. We can have in between 1.5 and 1, we have 1.25. And then we can get within between 1 and 1.25, and then we can get somewhere between, and then we can have actually a lot of, or actually infinite number of values. We can assume different or infinite number of values with this continuous random variables. So let's try to look at the examples of discrete random variables and continuous random variables. So again, discrete random variables are values that can be counted. So for instance, the number of cars sold at a dealership during a given month, it is 0, 1, 2, 3, 4, 5, and so on. The number of houses in a certain block, we can count that. The number of customers who visit a bank during any given hour. So that's also a discrete random variable. We can have some number of fish caught on a fishing trip, number of complaints received at the office of an airline on a given day. So those are examples of discrete random variables because they can be counted. On the other hand, a continuous random variable can assume, again, any value contained in one interval or more intervals. So we can think of like the height of a person, the time it takes to complete an examination, the price of a house. We can also say the amount of milk in a carton and the weight of a fish, for example. So um, notice that the that in continuous random variables, there are intervals. We can see decimals there if we're going to think of it, and we have fractional parts. So we can also have some examples like life of a battery. So we can measure it as precisely as we want. Notice that the life of this battery may be 40 hours, it may be 40.25, it may be 40 point something, okay, hours. So we may, for instance, if we're going to assume the maximum life of a battery is 200 hours, so we will let x, our random variable, to be um, the life of a randomly selected battery of this kind, which has 200 hours. So then x can assume any value between the interval of 0 to 200 because that's the assumed amount of a battery, for instance. So consequently, these x with the maximum with the life of a battery is a continuous random variable then. In this video, we're going to have our focus with a discrete random variable, by the way. Okay. So in a discrete random variable, we will let x to be the discrete random variable. Okay, let's have that as our common notation. And so capital X, or we'll call that big X, is used to denote the random variable itself, while small x's refers to the possible values of this big X random variable. So the probability distribution of big X, that's our random variable, describes how the probabilities are distributed. That's why it's called the probability distribution, because the probabilities are distributed all over the possible values of big X. That's our random variable. Okay, so all the possible values of big X are, of course, our small x's. So we can say that the probability distribution of a discrete random variable, also short for a discrete probability distribution, lists, okay, all the possible values that a random variable can assume and their corresponding probabilities. So I'm going to show you an example in a while. Let's take a look at our example before this. The number, okay, recall the previous example on the number of children in all 2,000 families in a small town. In this particular example, we will let x to be the number of children in a randomly selected family. So remember, we're going to select one family, right? One family, and let x be the number of children. So from here, we can say that x assumes the values of 0, 1, 2, 3, and 4. Okay, and we are tasked to write the probability distribution of this big X, which is our random variable for the number of children. So actually we already have these probabilities. How to get the probabilities? The relative frequency actually somehow kind of represent the probability. So we compute for the relative frequencies to be used as our approximate probabilities. So we have already that. So actually when the relative frequencies represent the population, they give the actual or theoretical probabilities of outcomes. So using the relative frequencies shown in this table, we can create a probability distribution of a discrete random variable big X. Or we can simply call that, the discrete probability distribution. So let's try to create one. So in a probability distribution, so you must have a header. Let's just not make it now. Let's proceed to the um to the table itself. So let's have first the X, our probability of our big X. So remember that big X, sorry, remember that big X, let me erase that, have the values of, that's our random variable. So we have 0, 1, 2, 2, sorry, 2, 3, and 4. Okay, and we'll be putting that in our first column for the random variables for its values. So let's create a rough table here. Okay, and we'll put 0 here as our first value. Oops, sorry. We'll put 1 as the next, 2, 3, and 4. Okay, let's fix that in a while. Okay, and we'll call the second column to be our probabilities of this random variable that we got. So let's call that p of x as our notation for probabilities. And what's the probability of getting 0? So we can see that in our relative frequency that the probability of getting 0 is 30 over 2000. We can put that in decimal notation. It's going to become 0.015. That's our number 1. Rather for 0. For 1, so we have 0.235. 235. For 2, we have 0.425. For 3, we have 0.245. And for our 4, we have 0.08. We can stop there. Okay, and then we can see that the summation, okay, I should have put it on the last row, but it cannot fit. The summation of all the p of x's is equal to 1. Try to add them all. Try to add all of these, and it will surely become 1. Okay, and that's one characteristic actually of a discrete probability distribution. So like I said, you should have the title above. So that's how we do the probability distributions for number 1, for our first example. So this is the probability distribution. Notice we have all the probability values of x, of big X, denoted by small x here. We have all these values, and then we'll get the probability of each of p of x, or rather each of x, and then we call it p of x, and then we just distribute all the values, and then it will end up with 1. Why did we end up with 1? We should, because actually that's why it's called a probability distribution, because we distributed the values, which is the sure event, the 100% into each of the random variables, and it should always be equal to 1. Um, we can do or move forward by making this a histogram if you want, but in this video we would just make it a raw graph to make things simple, but you can always use that histogram. The histogram is a standard actually. So 0.15 for 1, and then we have for number of children, rather I should think they should start with 0. This should be 1, sorry. This should be 2, this should be 3, and this should be 4. Okay, and then voila, but you'll have that. So 0 is 0.15. They should not be 0. 0.1, 0.015. 1 is 2.35. 2 is 4 0.425. 3 is 0.245, and 4 is 0.08. So there you go. Okay, so again, you can make use of a histogram if you want. And let's go back a slide before, and we'll be looking at the characteristics of a discrete random variable or a discrete probability distribution. So you may pause the video and then try to see for yourself what are the characteristics that you can see. Okay, so let's move to the next slide. The characteristics of a discrete random variable or a discrete probability distributions are as follows. Number one, the probability assigned to each value of a random variable in big X lies within the range of 0 to 1. That is, the probability of P of X, or the P of X, should be between 0 to 1 for each small x that we have. Okay, in each small x in big X. Okay, so it should only be between 0 to 1. Notice here, so the probabilities are all between 0 to 1. Okay, in this part here. Number two, the sum of the probabilities, the summation of the probabilities assigned to all possible values in small x is or must be equal to 1. So that's the summation of p of x must be equal to 1. Noted here that the summation of all p of x's is equal to 1. So indeed, the probability distribution is correct. Oops. And thirdly, the rod graph is used to represent the probability distribution of a discrete random variable. We can also make use of a histogram, by the way. Okay, so these are the important characteristics. More importantly, 1 and 2 are the important characteristics, actually. Okay, and that leads us to example number 2. Example number 2 will be, there will be a reserved video for example number 2. This is our a problem, so we can have that as an exercise. Maybe you can answer that in your own, get a piece of paper and try to answer that. And then, yeah, that will be your assignment for this video. So I think it's due time to end the video now, and in the next video we're going to continue our discussion with the expected value of a random variable. So thank you very much for watching, and I hope you'd like and subscribe.